Well, here's a new definition and a new way of looking at vectors. It's called the component form of a vector. If we want, we can assume the initial point of a vector is the origin 0, 0. Remember, this is just one of the many representations of that vector. But then we can notate the vector by writing the terminal point only in carets, like this, the vector AB. That's component form. And again, that's one of the infinite number of representations of that vector, but it's the one that has initial point at the origin. The 0 vector is notated with a boldface 0 or else 0, 0 in component form. And so what's the component form of our vector from exercise 1 or example 1? Let's see, component form of this vector. I guess it would be 3 minus 1 and negative 7 minus 5. So, or we could have said it like this, 4 minus 6 over 7 minus negative 5. No, sorry, this is initial point. So it'd be 6 minus 4 over negative 5 minus 7. Since this is initial point and this is terminal point, same thing, this is initial and this is terminal. So it would be the point, or the vector 2, comma, negative 12. That would be the component form of that vector. And so, hopefully, yes, there it is, in very tiny print, but hopefully you can read that. So that's the example, that's the quick example of that. Notation, the length of a vector is a scalar. That means it's a number. For example 1, if you recall, it was the square root of 148. And it's notated like this. Sometimes you'll see it like this with double absolute values. Sometimes in context, it'll just look like one absolute value symbol, like vector, if I put it in absolute value symbols, let's see, it'll look like vector V, or something like that. Sometimes I like to make it double absolute value symbols, but it doesn't matter. You'll pick it up out of context. If it's absolute value of a vector, then of course it means the length of the vector. So you may see it look like an absolute value, but don't worry about that. So here's a set of vector operations. If u in component form is u1, u2, and v in component form is v1, v2, and k is any scalar, that is any number, then vector u plus v is u1 plus v1 and u2 plus v2. I guess you would have guessed that. Scalar k times vector u is k times u1, comma, k u2. Negative u is just negative u1, negative u2. And I'm thinking I really didn't need to show you this because we could just say, yeah, but if k was negative 1, then that's what we get anyway. And u minus v is u1 minus v1, u2 minus v2, but I don't know if I needed to give you this because we could have just said add negative 1 times v to u. That would be the same thing. But anyway, this is how you, with component form, can add, subtract, and get a scalar multiple of a vector. It's hard for me to tell on my screen, but that k is not bold, the u is. And so that's vector, scalar k times vector u. Geometrically, vectors are added using the parallelogram law, and the added vectors are placed so that the head of one vector, I'm going to show you vector u added to vector v here. Here's vector u, or this is one of the representations of vector u. Here's one of the representations of vector v. And if you take the tail of v and put it up there at the head of u, like I did in this picture, then vector u and v and the vector u plus v, which is this purple thing here, form an oblique triangle. So that triangle, and the reason why it's called the parallelogram law is if I would have chosen to add vector u to vector v, in other words v plus u, I would take this vector and put it over here at the the tail of vector u at the head of v, and I'd get this. But notice that the vector u plus v and the vector v plus u are the same direction and the same length. So I guess we just proved that u plus v equals v plus u in vectors. But you can see now why it's called the parallelogram law, because look what this forms, a parallelogram. And oftentimes, to calculate the angles necessary, we might need to use the fact that there's 360 degrees in a parallelogram as opposed to 180 degrees in a triangle. So hence it's called the parallelogram law. Maybe if I can be fancy enough here with my software, oh, it's going to be hard. Bear with me. Here we go. I could probably show you capturing this vector u, and I want to cut that. Let me see if I can cut that somehow. Control. No, maybe I could just. Oh, I'm drawing. I don't mean to be drawing. Okay. I think I better quit that. Didn't help me. But anyway, what I wanted to do was capture that vector u and move it up there to vector v. But I believe if you look carefully throughout the rest of this web page, you'll see that I do have such a move done where it shows you geometric addition of vectors. So sorry about this one not being very accurate, but that does show you how to do that. Vector subtraction is just u plus negative v. So the parallelogram law is still useful, but technically u minus v is easier to think of as a directed line segment from the terminal point of v to the terminal point of u. In other words, u minus v has a head at the terminal point of u, and of course you have to put the tails of u and v together and then go from the head of v to the head of u in that direction, and this is the vector u minus v. Notice the director is over here on this side saying we're going this way, and of course you probably could guess v minus u is the same vector, only pointing this way, right? And again, if you look through the rest of the website, you should see a better geometric picture of that.